Today's section, volume again, but now using known cross sections. This corresponds to section 7.2 in the textbook. The known cross sections will be flush up against the base of our solid and perpendicular to either the x or the y axis. So cross sections with an area. So not a radius anymore, but an area formula. So let me show you kind of what I mean. So let's say there's a base that's triangular, okay? And imagine the triangle kind of lying flat. You're looking at it diagonally on the floor, so it's kind of a little distorted. Okay, it's not like a triangle like you normally draw, but maybe like that. Okay, kind of looking at it on the floor. Let me make a couple of copies of this. So let's say you're looking at a volume, but the volume of the object made of cross sections that are squares. Okay? And the squares have the same height as they do width or base. The base is kind of guided or mandated by the triangular base objects. So a square has the base and height that are equal. There's another square here. Base and height are equal. Another one here. Base and height equal. Another one here. Base and height are equal. And eventually, this object kind of a pyramid-looking shape, okay? Let's say the cross sections are semicircles. So a diameter and a semicircle. Diameter, semicircle. Diameter, semicircle. All the way down, and then this all kind of has a smooth outline to it. Alright, so you have kind of half of a cone there. Or let's say that the cross sections are equilateral triangles and the solid length is kind of guided by the base. So equilateral triangles all the way down. And those are not my best work. Yeah, the kind of sharp cone triangular, it points up at the top as it goes down. Or it could have their cross sections are rectangles, where the height is half the length. So the height is half of the length of the base. So the height is a third of the base. Kind of going all the way down. So using areas and then stacking those areas one on top of another to make volumes of shapes. So we're looking at, going to look straight down at the base now. So f of x, 1 minus x over 2. So 1 minus half of x. So down 1 to the right, down 1 to the right, and drawing that line. G of x is negative 1 plus x over 2. So 1 just up to negative 1. slope of positive 1/2. And then drawing a better line than that. So we have f of x, we have g of x, and then we have x equals 0, so the y-axis. So here's our region, okay? Now we want to find the volume of a solid where cross sections to the base are squares. So on the left side, there's a bigger representative rectangle that's taller, so the square will be bigger. But then as you go to the right towards x equals 2, the bases get smaller and the height of the squares gets smaller. Kind of like this one up here. So you got to know area of a square. Of course, area of a square is side times side, or side squared. So we got to find our side. Our side is the height of a representative rectangle that is perpendicular to the x-axis. So top 1 minus x over 2 minus bottom negative 1 plus x over 2. Combine like terms, 1 minus negative 1 is 2, negative x over 2 minus x over 2 minus x. So using that side, the volume will be the integral from 0 to 2 of side 2 minus x squared dx. Cross sections are now semicircles. Semicircle, half a circle, so the area is 1/2 pi r squared. R is half the diameter, or half of s. The top minus bottom, the length of any representative rectangle in this area. So 1/2 s, take the s from up here, 1/2 of that is 1 minus x over 2. So take that, put it into an integral. The volume will be from 0 to 2, the integral of pi. So 1/2. Got a bit ahead of myself. Let me start over. So 1/2 pi r squared, right? So 1/2 pi are constants. You can pull those out. Then from 0 to 2. Of our radius is 1 minus x over 2 squared dx. Now the cross sections are equilateral triangles. Okay, this is kind of a nice formula to have. Area of an equilateral triangle, √3/4 s squared. It's not the most important formula ever, but it's good to keep up your sleeve as a trick, you know. Once in a while, hey, area of an equilateral triangle, √3/4 s squared. Kind of know that. Used it at parties as an icebreaker, you'll be very popular, okay? So s from the first part, s is 2 minus x. So use that. The volume, integral from 0 to 2 of √3/4 s2 minus x squared dx. And I guess I could have pulled it with 3 over 4 out of the problem. So maybe I'll do that when I do the antiderivative and all the fundamental theorem. So take a look at those, check your answers with my complete notes online.